We've been looking at permutations. Permutations is where the order we arrange them is important. Combinations is where we don't care about the arrangements. It's just the number of ways we can select something. We're not going to worry about organising them into a particular group or anything like that. It's just how many ways can we select something. So the actual arrangement's not important. Okay, so we're going to arrange the objects in a line, but the order's not important. Well, clearly if we use all the objects, how many ways can I do it? If I'm going to arrange all the objects in a line, but I don't care what order. One, put them in a line. That's it. So we don't usually worry about using all the objects when we're talking about a combination. There's just one way of doing it, using them all. So we're only going to use some of them. Now, whereas A, B and BA are different permutations, they are the same combination. Because A, B, BA, as far as we're concerned now, is the same thing. I don't care about the arrangement, I just get in the two objects. Okay. So if I have 5 objects, I'm going to grab 2 of them, and I don't care about the order. Well, when it was a permutation, these were all the possibilities for 5 objects. So we've got A, B, A, C, A, D, A, E, etc., etc., etc. Turns out to be 20, 5P2. But if I now cross out the repetitions, because what I'm saying is A, B and BA are the same, so I've double counted it. A, C and CA are the same, so I've double counted it. So I'll just cross out all the repetitions. And you see we've lost that many. Well, what we've basically done is divided by the number of ways we could arrange the objects, because now I don't care about the arrangements. And so I divide by the number of ways we could arrange the objects. Now, here we had 2 objects, so I divided by 2 factorial. So it left me with 10 when I got rid of all those that are the same, just arranged differently. And just to show that this does work, let's have a look at 5, arrange 3 of them. Well, it's quite a few objects. If it's a permutation, there's 60 there. Now, if I don't care about the arrangements, then I should be able to divide this by 3 factorial. 3 factorial is, so I should be left with, okay, so ABC is the same as BAC is the same as CAB and ACB and so on. Let's start crossing them out. We shouldn't have any double ups now. They're all 3 letters and they're all different. None of them are the same. And if we count them up, sure enough, we did end up with 10. So to go from permutations, we divide by the number of ways to arrange it. In fact, some people think of permutations as the other way around, where they say, first of all, I'm going to work out how many combinations I have, and then multiply it by the number of ways I could arrange it. So they're saying we're going to choose combination, then arrange permutation. It's another way of thinking about a permutation. But we're interested about combinations. So if we have n different objects, we're going to only arrange k of them, not concerned about the order. It's the number of permutations divided by the number of ways we can arrange them, so k factorial. Now, npk, you may remember, we had a formula, n factorial on n minus k factorial. But now we're also dividing by k factorial. So our new formula for combinations, n factorial, n minus k factorial, basically the 2 numbers on the bottom add together to give the number on the top. Yep, you got a button on your calculator for that one too. NCK, which I think can be found on the multiplication button on a lot of calculators. But once again, it is important we know the formula that it comes from in case we get ones which aren't giving us specific numbers and so on. Alright, let's try one. Here's a classic problem that we see on telly every week. How many ways can 6 numbers be chosen from 45 numbers? And everyone gets really excited and they think they're going to become a millionaire if they get the right 6 numbers and so on. And it is, of course, a combination, not a permutation, because you don't have to get them in the right order. You just got to get the same 6 numbers that are pulled out of that barrel. So let's see. It'll be 45C6. So in factorial notation, that'll be 45 factorial on top. 6 factorial, number of ways you could arrange those 6 balls, times, what would the other number be?
39.
39 factorial. Got to add together to give the top one. There you go. There are 8,145,060 different ways that those numbers could come out the barrel. People say you haven't got a chance of winning. Come on. Now, just out of interest, I think it might have changed in recent years. I think we're still at 40 cents a game. So if you were to go and cover every possible combination and pay 40 cents, it'd cost you $3,258,024, but you would guarantee yourself winning lotto because you'd cover every possibility. Committees are combination, because usually you don't care about the order when you select people for committee, you just want to get people on your committee. So it's a combination. 5 people, we've got a group of people we're choosing from, 7 men, 4 women. And just like with permutation questions, often the very first question is no restrictions, because that'll become the bottom of your probability. So if there are no restrictions, then it's simply 11C5. There's 11 people, again, it doesn't matter if they're men or women, 11 people, and we're going to select 5 of them. So 11C5, which is 11 factorial and 5 factorial, 6 factorial, but 462 possible committees. All right, imagine if we're back in the dark ages, which used to happen, it really did, where they say, no, the committee, only males. Oh, you can't have any of those nasty women on the committee. They might make us think or something. Yeah, we couldn't have that. So all right, we've now narrowed it down. So instead of choosing from 11, we're now only selecting from 7C5, and now there are only 21 possible committees due to the Stone Age thinking. Look at that, could have had 462 different ones, but now only 21. But then they got enlightened and they said, no, we've got to have at least one woman on the committee, come on. All right, but again, keep in mind, complementary events. We have already worked out total number, no restrictions. And we've worked out how many only have male. Well, now we're saying at least one woman. The complementary event to that would be no women or all male. So I just got to subtract what I've already found. So 462 minus the male only committee would give me all the ones with only, well, with at least one, I should say. At least one woman in it. So 441. Now this one usually interests people. Not that, of course, that you're old enough to gamble and play card games and things like that. But a hand of 5 cards is dealt from 52. I don't know why I've come up with these numbers. Oh, 52. We're only selecting 5 of the cards. 52C5. There you go. 2,598,960 different hands that could be played in this random game, whatever it could be. What's the probability of getting, I don't know, let's think of some strange term, 3 of a kind, which might mean 3 cards of the same thing? Okay, look after the condition first. First thing we need to know is what we're getting the 3 of a kind in. Because we could have 3 aces, we could have 3 twos, we could have 3 threes, 3 fours, 3 fives, and so on. There's 13 different things that it could be. So 13C1. Which turns out to be 13, which is logical. So you think, okay, well, there's 13 different things I could have 3 of a kind in. But now that I've found out which one it's going to be, there's 4 of those in a pack of cards, and I want 3 of them. So times 4C3. But I now only have 3 cards. I have 2 to get from how many? 48. Why is it 48, not 49? Exactly. Did you hear that? No. Which was, if you make it out of 49, you might get the 4th of the 3 of a kind. Oh. And then you won't have 3 of a kind, you'll have 4 of a kind. So there's actually only 48 cards we could choose from here. So times 48C2, giving us a grand total. So probability, if you're ever playing this imaginary game that I've just thought up off the spot here, probability of 3 of a kind, it's 58,694. Sometimes percentages have more meaning. It's around about 3%, 3.2% of getting 3 of a kind. So let's have a look at one that did appear in a test, 2004. 4-person team. From 9 women, 7 men. How many ways can this team be chosen? So it doesn't matter about gender. So all up we've got 16 and we're going to get 4. So 16C4, 1,820. Probability that the team will consist of 4 women. So therefore, from the 9, we're going to get 4. So 9C4, 126. So the probability then becomes 126 of 1820, 9 in 130. Okay, so 10G, we're going to do the odd ones. Ooh, not 19 or 27 this time.